In Western New York and throughout New York State, you can find an engineering marvel that would change the United States forever: the Erie Canal. This canal system was built in the 19th century and is still in use today.
Opened in 1825, the Erie Canal was the first empire builder in our history. It was the only water highway through the long Appalachian mountain chain. Supplying a route for the settlers to go west, it gave them a means for shipping their goods back east. Overnight,
it was our nation's first superhighway, designed to use gravity and the pressure of water to move boats up and down along the canal. It's an interesting part of human history, and it relies on some really cool scientific principles to work. In this episode of Compact Science, we're going to explore the physics behind locks and how they work in a canal system.
I've got an old mule and her name is Sal, 15 years on the Erie Canal.
The Erie Canal is a human-made river in New York State, connecting the Great Lakes with the Hudson River, which then leads to the Atlantic Ocean. Running between Buffalo and the state capital in Albany, New York, the canal runs a whopping 363 miles. At its time, it was the second longest canal in the world. In 1817, workers began to build the canal, and it was not an easy feat. The Erie Canal needed to cut through fields, forests, rocky cliffs, and swamps, all without heavy machinery. The work was done by hand or with the help of animals like horses and mules. Thanks, Sal. The engineers designing the canal had a huge problem. The land that the canal was to pass through was not flat. Lake Erie, the canal's western terminus, is more than 570 feet above sea level. But the Hudson River, the eastern terminus, is a mere 16.5 feet in elevation. How are they going to lift and lower huge boats up and down the canal? They built 83 locks to do this. Locks let water and gravity do the heavy work of moving the vessels. These structures allow the boats to be raised and lowered by changing the level of the water beneath them. Throughout the canal, there are watertight gates known as floodgates. A lock is the area between two of these gates. A vessel enters the lock and the floodgates close. The water is then raised or lowered via sluices, channels that bring in or take out water from the lock to raise or lower the boat to the level that's on the other side of the lock. Once the water levels are even, or in equilibrium, the boat can continue its journey. What's amazing about this is something water just does on its own. In a closed system, the water levels will equalize, or level out. Now, you may be wondering how the water knows which way to flow. This is where Pascal's law comes into play. According to Pascal's law, changes to a fluid, so a liquid or a gas, in a closed container will be transmitted to all parts of that fluid. So if the water level lowers on one side of a closed system, the same thing will happen on the other. The pressure from the water pushes against the walls of the lock evenly, causing the water level, and the boat, to rise or fall. How cool is that? Canals have played an important role in transportation and commerce for centuries. The Erie Canal changed the face of the United States. Boats and barges traveling west through the canal carried settlers from the East Coast to the Midwest, encouraging people to move to Michigan, Ohio, Indiana, and Illinois. Goods were able to move much faster from New York City to the Great Lakes. The Erie Canal cut the cost of transporting goods westward by 95%, and it cut the time to ship those goods by 80%. And it's all made possible by physics. The next time you see a canal, think about all the amazing engineering that went into making these systems possible. Pascal's law plays a crucial role in the operation of locks in a canal system. Blaise Pascal was a French mathematician and physicist who discovered this principle in the 17th century. He found that pressure applied to a fluid in a closed container is transmitted equally to every point in the fluid and to the walls of the container. Let's take a closer look. Here we have a series of interconnected tubes of various shapes and sizes. I've also added some dye to this water to make it a little bit easier to see. I'm going to pour the water into this widest tube. Which tube do you think will fill up first? Oh, did it? Yo, look at that. Look what happens when I add water to one tube. Notice how the water level equalizes. The water level at the top of each tube is the same. It's all about pressure and force. How cool is that? Pressure is the amount of force acting on a given area. So liquids and gases, known as fluids, are the two types of matter that go through continuous and noticeable changes caused by pressure. Think about it. When you blow up a balloon, you force air inside the balloon through a small opening. The air spreads out and presses against the inside of the balloon, forcing it to expand. Okay, so now we have a better understanding of Pascal's law. And we saw how this principle of physics allows locks to lift and lower boats to help them navigate through a canal. But where else can we see Pascal's law at work in our everyday lives? Hydraulic lifts, like the ones in car repair shops. Hydraulics transfer forces from one place to another through a liquid. They're used in many types of machinery. Drinking straws. Sucking on a straw creates a low pressure area, which is transmitted equally through the liquid in the straw and results in the liquid being pushed up and into your mouth. Even water guns work using the principle of Pascal's law. When you pump the gun and pressurize the water, the high-pressured water is distributed equally through the nozzle, creating a stream of water and a lot of fun. Understanding the principles of physics allows us to create amazing feats of human engineering, like the Erie Canal and the Lockport locks. If you're interested in learning more about pressure in liquids, check out our Compact Science Viewer Challenge. We have a fun experiment that you can try at home to amaze your friends with water that flows uphill. Get all the instructions on our website and be sure to share back your results in the comments. I'm Sarajane Gomlak-Green, and you've been watching Compact Science. Until next time, stay curious.
Compact Science is funded in part by the Joy Family Foundation and by the New York State Education Department.
In Western New York, and Mulligan. Sorry, my bad. Okay, we're good. I was so bad. Oh, bridge, everybody down. Okay. Don't leave! Stay here! We have candy! No, we don't.